My name is Frank Land, and I was a project manager for the RCC repair project from the time frame of 2005 through 2010. Prior to the Columbia accident, I was actually in Johnson Space Center Engineering Director under the Advanced Development Office.
My name is Ben Greene, the Johnson Space Center here in Houston. I work with the Crew and Thermal Systems Division as part of the Engineering Directorate at JSC. In the 2004-2005 timeframe, I was asked to join the RCC repair team as the engineering project manager.
Hi, my name is Dr. Scott Parazynski. I was an astronaut for 17 years and flew on 5 space shuttle missions. Also served as the lead astronaut for space shuttle inspection and repair in the aftermath of the Space Shuttle Columbia accident. Currently, I'm the chairman of the board of the Challenger Center for Space Science Education and am the chief medical officer for the Center for Polar Medical Operations, overseeing screening of candidates that will travel to the Antarctic continent.
My name is Alvaro Rodriguez. I work at the NASA Johnson Space Center, and in the 2003 to 2005 timeframe, I was a deputy NASA subsystem engineer, working on the leading edge structural subsystems. So that basically comprised all of the reinforced carbon-carbon panels on the wing leading edge and nose cap of the RCC, of the Space Shuttle Orbiter. I actually started working on RCC, prior to the accident, so I was becoming familiar with the different components. But when the Columbia accident occurred, became part of the team immediately as far as helping in the reconstruction, trying to understand what the causes of the accident were. So we were doing thermal analyses, we were doing investigations of hardware to understand, piecing together the puzzle of what transpired during the accident.
At the time of the Space Shuttle Columbia accident, I was assigned to mission STS-118. I just finished my tour of duty as the chief of the EVA branch in the crew office. And actually I was assigned to the very next mission of the Space Shuttle Columbia. It was to be the first and probably only Columbia mission to the International Space Station. And I remember vividly watching that day, and my heart, along with the rest of the Johnson Space Center and the nation, ripping out and wondering what would be next for the space program, not just our own little future as a crew of STS-118, but where things were going to head. And it was a very personal loss for all of us, not just members of the astronaut office, but I think everyone here at the Johnson Space Center felt an enormous sense of loss. Even if they had never met that particular crew, they might have seen them across the cafeteria and knew who they were and felt that they had a part in that mission. Everyone who was part of the space shuttle program feels a great, deep ownership of it. But I think it really was driven home when we lost that crew on February 1st, 2003. And it really galvanized all of us to focus on figuring out what had happened first and foremost, but then how could we prevent it from reoccurring, and then ideally, if something did happen on orbit, would we be able to fix it? And so very quickly, since I wasn't going to be flying anytime soon, I was assigned to be the lead astronaut for EVA inspection and repair. And we really didn't know what we were doing when it all started. We had a bunch of kind of scattered meetings as teams galvanized around this topic. Obviously, there were folks from the Mission Operations Directorate, from safety and materials, engineering. Crew office was integrally involved. And we tried to organize ourselves, and I think it came together remarkably quickly.
Shortly after the Columbia accident, we did not have a clear idea of the cause of the accident. We understood that the thermal protection system had been compromised, but what subsystem, whether it was the tile or the RCC. So there was a tremendous amount of activity to just understand the root cause, to understand the role of the reinforced carbon-carbon, the wing leading edge panels, whether they were penetrated, and so we developed a lot of testing and analysis as part of that effort.
We were developing materials that had never been developed before. I mean, NOACS was something that we basically developed from scratch. We had materials that were pre-ceramic polymers, but the mixing of the powders and these different materials that went into those polymers to essentially cure on entry and form a ceramic on the wing leading edge, just that hadn't been done before. There was a feeling that the problem we were trying to solve was not solvable, and I think that early on we were kind of asked to go off and solve something, and I don't think anybody expected to hear back from us, frankly. And so a lot of focus at that time was being put onto tile repair techniques. And so when we actually did start showing success in the arc jet, I think that did surprise a lot of people. Given that there is still a possibility that we could liberate some foam or ice or some ablator, there was still a chance that we could get damage to the RCC that could result in catastrophic failure of the RCC system. So we did have to go out and develop some techniques to be able to fix different types of damage on the wing leading edge.
During the summer, after we had assembled multiple experts from across the agency, material experts, we had put together a suite of potential candidates for repair techniques. So an organization was put together, and based on the list that we'd gone through, as the deputy of the NASA subsystem engineer, I became involved with the accident investigation, and that involved impact testing as part of understanding whether the RCC subsystem was part of the root cause in the destruction of Columbia. Then there were efforts and teams that we got involved with in terms of the repair team, developing inspections, determining the damage tolerance of the RCC. And all of these teams were going in parallel. There was a lot of, I'd say, organized/unorganized chaos going about the assembling of these teams, who were the core members, and how to proceed, whose data needed to feed what team. During this period of uncertainty, the RCC, the leading edge structural subsystem problem resolution team, had a role in helping all these myriad of teams that were being formed. We wanted to bring our expertise on the hardware itself. So, what are the constituents of the material, our understanding of its thermal performance, our understanding of how it breaks, and the aerothermal performance. And so to each one of those teams, we had different questions coming in. How does, for the inspection teams, what does our material look like? What does it look like when it's damaged? For the impact tolerance teams, what kind of models do we have existing for the structural analyses? In our material properties, what could we help yield that would benefit those teams? And when it came to the RCC repair team, one of the biggest attributes, or one of the things we could help out a lot with, was what kind of environments would you expect a repair to be subject to? So that means if the RCC is getting to be about 3,000 degrees Fahrenheit at the hottest part, how is a protuberance, a carbon sick plug or a NOAX putty going to perform when it's sitting on top of that RCC panel? So that was one of the things that we tried to bring to them. Also, our knowledge of how you test these materials, either an arc jet, radiant, any kind of structural testing, things that we had learned along the way with our testing of RCC. So there was continued testing that was going through the summer months of 2003 that had to do with impact testing of RCC panels. And one of the major tests was an impact test on panel 8 on the wing leading edge stand. And they were able to generate a 16 by 16 inch hole on the lower surface of panel 8. So from there, we knew that high-speed impact with foam could generate catastrophic damage, and that sent the focus on the RCC repair team became much more heightened. So now, during that summer and shortly thereafter that impact test on Panel 8, our structural engineering division had pulled together a technical interchange meeting between multiple centers and multiple material experts to bring together expertise on materials that could be leveraged to repair RCC. Following the impact test of Panel 8, where we had generated a 16-inch hole, that provided us our first data point of the kind of damage that could potentially exist with the foam liberation. We had teams from, we had material experts from across the agency come together and who brought, ideas, concept, materials that they could put together for a potential repair option. Based on the kind of damages we would expect that range from very small to very large, 3 major concepts were put together. That was the RCC rigid overwrap, the RCC plug repair, and RCC filled wing. Early on, all of the teams did not really have the kind of requirements they needed to really kick off the projects. They were hamstrung by the fact that we were just getting started on defining the damage tolerance requirements. So how much damage could RCC sustain in terms of either breaking the initial outer coating of the RCC or through penetration? How much damage could it sustain before it required repair? That's an important concept because you don't want to actually have people leaving the vehicle and getting close to, in proximity to the wing leading edge and repairing it if there was no need for it. So those are important requirements that we had to define. Those requirements did not get pulled into shape to really feed the teams until much later. They required extensive materials that we had to obtain. We had to assemble test fixtures and really kick off those test programs. And I'd say the first good bit of data that we'd gotten on small cracks and penetrations didn't really come into fruition until late 2003, about the December timeframe. We were really going back. The requirements that we were feeding the RCC repair teams were based on our experience over the years dealing with RCC, and the one or two data points that we'd had from the impact test at Southwest. Now there are more impacts that were scheduled and that started to kick off. So after they had created the hole in Panel 8, there are more panels that they had to destroy or to initiate the impact tolerance for the panels. How much impact could you impart on those panels without even creating a visible damage? And so all those studies and testing were going along in parallel with the idea of we want to generate a repair concept and have that flown as soon as possible.
So what we have here is an actual flight article which we factory flew on STS-114 with all the plug repair hardware for the RCC repair. What we have here is essentially there are a total of 19 plugs that's in this bag right now, but on STS-114, we actually flew only 13 of these. The plugs look similar like this. Because of the different curvature on the RCC panels on the vehicle, what we had to do is we had to go ahead and design different curvatures of RCC plugs, and as we install them, here's an example. As we actually assemble the repair plug and we put it through, we drill the hole in the RCC panel, we insert it through, as an astronaut would do. As we torque up this bolt on the top, as the astronaut turn it, this T-bolt here will actually move up, and it actually becomes perpendicular to this shaft right here. Eventually draws up to the backside of our RCC panel, very similar to what you would do normally at a home repair for a drywall repair. Similar concept. That's exactly what you would do. Okay. Once we do that, the astronaut will continue to torque it until this plate conforms to the RCC panels. We do have a gap gauge that we use to make sure that the gap does not exceed, I believe, what's 20,000, okay, of a gap. Okay. In addition to that, what we have learned during testing was that to ensure that we do not have excessive gap, or we don't want any gap at all, we also use our crack repair material as sealant around the edges to give us the extra additional confidence. in addition to sealing the edges, what we would also do is we'll also put a dab of the no-accident repair material on top of the bolt. This would provide us additional thermal protection on the bolt to keep it cooler. Okay. So, like I mentioned before, there are about we actually have total 19 different curvatures. The first 13 that we flew have curvatures like this or like this. Okay. But what we did was, as development of this, the design of our CC plug repair continues, what we found out was that the initial design that we had wasn't the most optimal design. What we ended up doing was, by reorienting the fabric as we manufacture the plugs from 90 degrees to 60-degree layout, we were able to produce only six plugs to cover 90% of what 13 plugs would have covered.
When I joined the team, there were three main concepts being pursued at that time. There was the large overwrap repair, where we were actually going to have these very large, essentially RCC replacement panels that are like very large taco shells that were going to replace the entire panel. Then we had the plug repairs, which would repair about a 4-inch through hole in the wing leading edge. Then we had a liquid repair that would repair cracks in the surface, very small type damages that would really just be talking about the kind of surface damage. So at that time, the overwrap repair, this very large repair, was starting to phase out. We started focusing really on the plug repair and the crack repair, the liquid repair material that would eventually get us to where we ended up with 114 and 121. But at that time, we didn't have any real requirements set. We were still kind of in an R&D phase, and so we started focusing on developing a good set of requirements for the plug repair and the crack repair system.
So the first repair option, the RCC rigid overwrap, met significant technical difficulties with concern to the attachment mechanism and also the mass and volume of it. It was too heavy and too large to fit all of the overwraps that could accommodate all of the panels. The second one was the RCC plug repair, and that actually continued. That showed viability in the ArcJet test. It had materials that could survive the temperatures. The third, the RCC filled wing, was technically challenged from the beginning. One is the concept of filling a hollow RCC panel structure with a material would prove to be would make the material too hot, because you would not have the cross radiation that the RCC thrives off of. So the materials, though, that were brought up in the RCC filled wing concept, however, did show promise as crack repair and as a means to repair the coating of the RCC. So those types of materials, the liquid RCC repair materials, were taken forward, and that eventually became the RCC crack repair.
So as part of our mitigation strategy, we really had to put together a pretty broad team of experts. So we brought in a good material science team from Marshall Space Flight Center, and they concentrated on doing the development of the NOACs material, controlling the different powders and the polymers that needed to go into that material. We also brought in a team from ATK that concentrated on design and development of the plug itself. So we had those two different teams working. We had a JSC team that included a group from the MOD, our ops group, had a crew representative, and all of the different project management folks here at JSC that kind of brought all that all together.
Top-level mitigation for RCC repair as well as tile repair involves the human element, buying down some of that risk by ideally increasing training or having the ability on orbit to train a crew. Ultimately, in an ideal world, we'd love to have additional time and to develop other materials or to further characterize them using detailed test objectives, to do experiments on orbit and gain further confidence. But we didn't have that luxury in the shuttle program. We had a very short runway of a few more flights to finish the International Space Station assembly sequence, and that was it. So we developed a cadre of folks who had done a number of vacuum chamber runs and developed the procedures here on Earth, and we were available to coach the crews on orbit should they ever need to do these repairs.
In verifying the performance of the RCC repair options that we had on the table, there were a lot of variables at play. Those included temperature, pressure, shear pressure, the oxidation environment, the location on the panel, which set the curvature, which set how hot the RCC panel would be at that location, the kind of protuberance effects you would get from the aerothermal environment. So in order to bring those variables into a manageable set that you could work with, we defined a smaller scope of design reference cases so that identified a specific location on the vehicle with a specific set of thermal gradients, a specific set of aerothermal heating, that with a set of damages that we would look at for each case. And with that, we had 3 different design cases, which helped out the team in developing its VNV plan. So the design reference cases really built a set of test data. While they were at discrete locations on the wing, they had relevance to other locations. So one of the worst cases you had was on, say, a panel 9 on the lower surface that had temperatures up to 3,000 degrees. Well, if your material, say the crack repair, was highly dependent on temperature, then and you were able to pass with a certain set of damage conditions and repairs of those conditions, then you could say a lot about the temperature performance across the majority of the wing. So the design reference cases still had relevance for even locations that they were not at.
I took over the RCC project in 2005 at the request of the Warburg project manager. At that particular time, I didn't know what I was getting into. I was familiar with RCC panels. I know about RCC system because I worked the system at KSC. However, I knew that repair RCC on orbit is not going to be an easy task, and it's not going to be something that would be achievable without a significant amount of resources being invested. As RCC repair project manager for the program, I have also several different project managers that assist me, making sure that they deal with the day-to-day technical issues, such as Ben Greene, the engineering through crew and thermal systems. He's mainly focused on the overall system requirements as well as all the EVA tools aspect of the repair project. And then we have engineering of structural systems, thermal systems, Alvaro Rodriguez, and also Dr. Don Curry at the time. They were the main focus from a standpoint of the technical from RCC hardware itself and how this repair would affect the hardware and how it's going to affect the entry of the orbiter.
We're very fortunate to have really well integrated teams through the TPS repair effort. We had obviously mission operations, engineering, safety, but we also had the hardcore science teams, material scientists at Langley and Marshall and elsewhere, who were down and in and proposing new materials to meet these challenging requirements. We had, thankfully, in the astronaut corps as well, folks who had been aerodynamicists and material scientists and failure analysts in prior lives. So we're able to engage on a number of different levels. And certainly we were not the material scientists experts that did the down and in work, but we were able to understand and speak some of their language and then also share with them operational principles that would have to be levied upon use of these materials.
One of the big lessons I had learned through this, going through the repair project and seeing it to success was the value that we had in the team members and learning how to divvy up the roles. We had to learn how to, especially for mission support, how do we work with each other and how do we trust and rely on each other to all come together to ultimately make a recommendation and to the project. And a lot of that was building trust with each other in terms of our technical discussions, even personal relationships that we had built up. Those were invaluable. At the end of the project, I felt confidence not only in the data that we had generated, the design concepts that we had developed, but really in the personnel that we had built up around this project. We had very close relationships in terms of building confidence in each other so that we could accomplish a potential repair. From this experience, one of the lessons that we learned in the communication within the team, the RCC repair team, was the involvement of the hardware owners as part of the team structure. So at a top level, we had the project management for the RCC repair team, but integrated into the team was an LES, so the leading edge structural subsystem membership, would be part of the decision-making process and part of the technical discussions. So one of the lessons that we learned in communicating within the RCC repair team, we found it very valuable to include the RCC hardware owners as part of the team, included into the membership, because there were a lot of questions about technical requirements, how to interpret, the types of damages, where to find the right information for the environments. And so the RCC hardware owners as part of the team, I thought, was critical.
Another key aspect of this lesson is that we took our team everywhere, really. I mean, and it was a very cohesive team. In fact, we had people that left the project that would come back in the event of a real-time repair. If we actually had to perform a repair, these folks that even in some cases had left the agency had offered to come back and support real-time repair if we ever had to go perform one. So I don't think that there was a time when we never had a quorum, essentially, from a team perspective. We were always working together across the different disciplines, the SNMA community, the engineering community, the structures group, the different contractors. We were a very cohesive repair team, and I think that it actually showed in a lot of our work.
As the RCC project had to deal with more cost constraints, the burden of performing analyses and testing started to rest more on the civil servants. So in order for myself as a hardware owner to get the necessary data on, say, the thermal performance of the plug repair for multiple environments, that really meant I had to build a thermal math model that had the right geometry. And then we had to define the test to go, shore up that thermal math model to show that we had test data to correlate it to and to demonstrate the success of that model. That rested on ourselves at some point. When we started to lose our contractors and support, that meant we had to spend extra time to accomplish the analyses and the test. And it was valuable in terms of being more you felt more connected to the hardware. You felt more in tune with the performance of the hardware as you watch those tests progress and as you perform more analyses. So I felt it was critical for us to be involved with that. The hands-on approach, I think, has a lot of benefit to engineers.
As another discussion with respect to requirements, whenever the team actually started realizing that we didn't have to dispense as much material, and we were getting a little bit of restriction on our resources, that we could actually get by with commercial off-the-shelf equipment. So this is actually an off-the-shelf caulk gun that ended up being flown on STS-114 and STS-121. It's just that's a custom thermal cover, but we were able to just use off-the-shelf equipment to actually apply the NOAX material to the wing leading edge. Using commercial off-the-shelf equipment makes a lot of engineers uncomfortable because your team was not involved in the actual development of the hardware itself. So there's a lot of different variables that we may or may not know about this equipment. But in this case, it was a cost-effective, inexpensive way of actually getting the material from onto the wing, actually. And so this there's nothing wrong with using COTS equipment in flight hardware development. T&V was actually a very complicated process. We had an arc jet at JSC that had a very specific chemistry and a very specific environment. Well, it had a lot of different capability, but it had a specific chemistry, and it was different than other arc jets that we had access to. Early on, we did a lot of testing here at JSC and thinking that we're covered there. The JSC arc jet envelopes what we're testing. And when we started branching out and going to other facilities like Ames, we realized that these different environments really do have a different effect on our results, and maybe we really ought to look at that better. We started looking a lot closer at the different models that we were using for analysis of our repairs and the different structures and the RCC itself, and realized that we really needed to go back and do some characterization of not only our test environments, but probably going off and getting some more data to feed the models and do a bit more validation of those models that we were using. It led to another set of tests that was actually going out to get more data to go validate our models.
One of the lessons that we learned and had to do with our testing, and it really had to do with, up front, we would have been better served if we had characterized our testing facilities ahead of time, had developed the right relationships beforehand. I think what transpired in the repair project is, we would run into either an issue in terms of scheduling, cost, or technical issue with a facility, and then have to redirect our focus to another facility. Meanwhile, we had not fully characterized the environments, and that led to problems. So a lesson learned would be to identify the testing resources, testing facilities that you would need to accomplish that, and all of the facilities that you could possibly use that would meet your technical requirements, and to characterize them ahead of time so you can understand where you are best suited to apply your different tests and for each facility.
It was really remarkable how quickly we got into test environments. First off, we developed high-level strategies for repair and how quickly we got into these test environments, including the neutral buoyancy facility, neutral buoyancy laboratory, or NBL, a large swimming pool where we practice spacewalk techniques, aboard the weightless aircraft, parabolic flight, where we tested the deployment of various types of COTS and repair strategies, and also into vacuum chambers. So we were testing within the first 3 or 4 months after the accident. So as I said earlier, the teams came forward with a bunch of great ideas. Some of them were blue sky, never going to work ideas, and we were able to fairly quickly discard those. But when we got down into the weeds of some of the other solutions, it wasn't nearly as easy as we would have liked.
Given how important RCC repair is to the success of each mission, each mission required an ability to repair, potential damage. There were aspects to the repair project that were dependent on either small companies or, single source items that we had not envisioned would be a problem because we had been so focused on the design and development and coming up with a great solution to a seemingly impossible problem. But as we kept rolling through the missions, this became an issue. We'd have issues with our powder lots, that we were procuring from Germany. We had issues with our resins that we were procuring from, a small company, and that presented challenges. So we had to come up with extraordinary means to either keep the companies, viable, or to make sure we procure enough of the material so that we could serve out the remainder of the manifest.
We had a well-thought-out set of requirements, but that did not mean that we really had a well-thought-out T&V plan. And so the T&V plan, the VNV plan, really came together as a group. We had the different product teams developing the hardware, and so they knew what they needed to test from their side. And then we had the group from the Leading Edge Structural System Problem Resolution Team, the LESPRT, that more or less organized and kind of led the direction we were going, because they were working out all the different types of damage and the environments that we would have to experience. And so we ended up developing a set of design reference missions rather than just having this very, very broad set of essentially infinite configurations of test. We specified a specific 3 that we would have to go meet. And even within those 3, there were a lot of different variables that we had to go out and define. And so because that was a two-way street there, we had different types of hardware that we wanted to test from the product teams. Then the LESPRT would provide us with those environments. And then as a team, as a group, we really developed the overall VNV plan. I think it worked out very well. The two different repair techniques between NOACs, our crack repair, and plug, which was our through penetration repair, really had two completely different development methods and verification methods. The plug repair was a mechanical design that was easily drawn up in CAD. You could actually go and manufacture, and you had a very solid, non-abstract piece of equipment that you could actually test, analyze using thermal tools, different structural analysis tools, very, very defined set of equipment that I, as a mechanical engineer, feel very comfortable with, because it, like I said, it's very not abstract. It's a very understood piece of equipment. So from that perspective, we knew all the variables we needed to go out and define. That being said, because we knew what all those variables were, there was a number of them, and so it required a lot of testing. So from the NOAC side, the crack repair material, that was quite a bit different, because even though we knew what a lot of the variables were, there was an infinite number of them. We could never test every single configuration of a repair that a crew member would affect on the wing leading edge. So in this case, in the NOAC's case, we actually went out and defined a number of tests that we would use as what we call confidence tests. And we basically tried to do an empirical type of verification rather than an analytical one. Plug repair was very analytical. We could go out and do a small number of tests with the plug repair and actually get a good set of data that we could fill in the rest of the holes with from analysis. On the NOAC side, we had a very opposite situation where we had very little analytical capability, but we had a huge number of tests that we went and defined, and actually did end up doing more than 100 different ArcJet tests to fill a matrix of confidence tests that we would be able to go back and reference during a real-time repair. As engineers, we always want to analyze everything, and so we did not think at the beginning of the development of the NOACs that we wouldn't be able to analyze it. In fact, we did try in the beginning to develop an analytical model for the NOACs. We defined a specific set of variables that we needed to go out and develop adhesion capability, what different types of contaminants would affect the repair, what would porosity do to the repair, and in the end, when we tried to actually take all of those variables and develop the model, we just weren't getting good repeatability. We weren't getting good predictability with the model. And so from that standpoint, even though we might have started in the wrong direction, thinking that really, if we had started in an empirical path from the beginning, we might have gotten some more testing accomplished, and that might have been some resources that could have been spent in a different area. So a key lesson for the development of a lot of these repair techniques was to keep a separate set of folks off working new techniques all the time. So even after we had chosen two repair techniques in the plug repair and the no-ax repair, there was a team of folks off at Langley that were always looking at new and different ways to improve what we were doing, coming up with new techniques, different type of repair techniques. There was one called the small area repair, which is essentially a mini plug that would only require a small, 2.5-inch disc with a threaded bolt to repair small damages similar to what the crack repair material would repair. They also developed different tools and techniques and some of these drills that we would need to drill out a hole in the RCC and perform a plug repair with. This came out of Langley as well. So it was always a benefit, and they were constantly coming up with new, different things that kept us thinking about different ways of performing different repairs, and so there was always something to learn from that team.
All astronauts are trained generically to do a variety of tasks, homing in on the Space Shuttle and Space Station program. So there are mechanical interfaces primarily, handrails, translation, electrical connectors, fluid connectors, turning bolts. What was interesting about the TPS repair challenge is that we're now called upon to use tools that were never imagined to be used in space, using fluids that we're going to cure in place, and having to work with materials that we're curing with our assistance. So working with a myriad of brand new tools, unlike anything that you have in your workshop, was an additional challenge to our spacewalkers. We had to develop dozens of new tools for both the RCC as well as the towel repair. And it required a primary operator and then an assistant or a scrub nurse, if you will, to hand tools back and forth, and it required a lot of coordination. It also required a lot of situational awareness, working in close proximity to very sensitive structures, right up against the very materials that were going to bring you home safely, hopefully. So we had big robotic arms and big dispenser guns and things that, if you're careless at all, you could actually make things a whole lot worse. One of the lessons learned for going forward in spacewalking is if you can make the interfaces as common as possible, familiar to your workshop at home, the more bells and whistles that you try and design in, the more failure modes that you have, and potential for misuse as well. So I think the more you can make things common user interface, the better. And also to get crew input early and often, I think really helps buy down the risk of tools not being operable in that environment.
So one of the key lessons that we learned was we needed to have a very good real-time support plan ready for mission support. So when the real day comes along, you actually have to go and effect a repair. There's a lot of little things that can go wrong, it can go right, and without a careful plan in place to deal with those different little scenarios, it's a very chaotic situation. So we performed a lot of sims leading up to STS 114 and 121, where we did learn quite a bit about what to expect and how to plan for that specific mission. So one of the most important documents that we did actually develop for both the RCC crack repair and plug repair was a real-time support plan. And that plan laid out in very specific detail when we needed to start specific analyses. One of the really important things for no-ax repair was once we actually applied the material to the wing, it had to cure. And so we had to have time and get the orbiter in the right orientation till we get some sunlight and actually get a passive cure from the sun to that material on the wing leading edge. The amount of cure that you got on that material was actually a factor in how well it performed. So that plan would lay out when we needed to start talking to the different contractors about performing that analysis. It set bingo times for when we needed decisions about certain things. We would communicate back to the mission management team how much time we needed to actually perform the repair and then still have time for the repair to cure. And so again, another time was laid out when we needed a decision from mission management team on go, no go for a specific repair, when we needed to be out actually repairing the wing, going out for a second EVA to perform any kind of checks on the repair, verifications, if you will. And in a lot of cases, we relied on the OBSS, the Orbiter Boom Sensor System, to go and do some analysis for us. So all of that interaction that was required between the different product teams, the LES, SPRT, and the mission management team was laid out in that document very well.
Let me focus a little bit on risk. During operational, real time, in the event we do have a damage on orbit that requires a repair to be done on RCC panel, it's not going to be something that will be taken lightly. The MMT has first decide whether or not it's want a repair, want an EVA, mission objectives to send a crew member, 2 crew members outside to go do a repair and potentially introduce more harm to the RCC panels by putting in the plug. Because you actually have to drill a hole to put a plug in versus a NOAX repair that you can just go ahead and slather some material on here. So the decision has been made early in the flight to allow the damage assessment team as well as the technical team and the repair team to go come up with the right technical approach and right procedures so we can uplink to the crew so they can go train and execute. Okay, and then we got to verify the repair and then report to the MMT before we can say we have the confidence to come home. So the pressure is on during the operational time frame. So when you talk about risk, everything is about risk on RCC repair. The approach that the team took, instead of quote-unquote calling it certifying the repair, what we did, we took a risk mitigation approach. We approached the management team and we told them that it would be better if we approach it from the standpoint of risk mitigation. Here is what we can do to show you what a repair can do. We focus on the design reference missions, on the design reference points on the vehicle. So we got enough testing data to show that, hey, for these type of scenarios, we have data to show that it's good. Okay, but we cannot cover everything. Okay, so all this data that the empirical data we have gathered pre-flight is going to help in making the case to the management team that, hey, we have the experience in doing this type of test, and we have shown that this repair itself it can sustain the entry environment, therefore it's going to be okay. So that's kind of a risk discussion that we would have in real time with the management team. Let me give you a good example on the risk mitigation or the discussion we would have during the MMT risk simulation. We were giving a through-hole damage on RCC panel. After exhaustive investigation and assessment, it was determined that the NOAX repair would be adequate to repair this based on its location and the size of the damage. However, once the decision was made and was given to the MMT, the SimSup, which is the simulation supervisor, decided to give us additional challenge and gave us essentially told us that the imaging detection team had made an error. The size of the damage is actually larger, slightly larger than what was previously anticipated. The team took that information back, reassessed the damage, and determined that whole site by itself is just not going to, the NOAX repair itself is just going to be adequate to repair the damage, and by no choice, without any other further choice, we had to go ahead and go to a plug repair. Once we informed Orbiter project manager regarding the new decision to implement a plug repair versus a NOAX repair, question from a lot of from a board member was why? We are only talking about a minute increase in dimension. How is it that you were okay with the no-ax repair, and now you got to go through a more extreme plug repair? The team was really on the top of this, and the reason is because all the testing that we have done have given us the confidence that up to a certain amount of the hole size, penetration, that we are able to repair with the no-ax repair. With the hole size now slightly larger than what our experience base, the team just does no longer have the confidence to be able to extrapolate that test data to say that we now have the confidence to say that this can come, that repair will be able to come home. So therefore, the damage team, as well the repair team, recommended to use it with a plug repair, because we know that plug repair, even though it might be more, create more damage to the RCC panel, but we know that for the load of it, the location of the panel, also the environment of the damage, entry environment, we believe that the plug repair will give us a higher confidence than try to extrapolate outside our database, experience base. So the lessons learned from our simulation and through this experience was that one should not extrapolate too far by your experience base with so many different variables that you just not know. Okay, if we understand all the variables, and we understand our test database, and we have confidence with our test data, and let's say it's more of a 3 sigma case, then perhaps we can stretch it out further. But in this particular case, we just were not ready. The test data that show us is what we currently have, but there were so many different variables associated with those test data that we're just not comfortable with extracting, beyond that database.
From a crew perspective, I felt reasonably confident that for the right type of failure to the TPS, either tile or RCC, we could ride a repair home. But there were certain very obvious limitations to both strategies. Depending on the location of the damage, if it was over a very critical part of the belly of the orbiter where there's very thin tile, you didn't have much margin. Over the external tank doors is one very critical area, for an example, and the gear doors being another. RCC, we just had very limited capability, quite honestly, to repair the wing's leading edge. If you were to think back to what happened to the Space Shuttle Columbia, there's a test done at the Southwest Research Institute where they fired a cannon of foam at the wing's leading edge and generated, I believe, a 16-inch hole in the wing, which would have been far in excess of what we could have ever repaired. So on the plus side, we had the ability to go to safe haven aboard the International Space Station, which means that we had the ability to keep the crew on board to either fly them home on a subsequent shuttle flight or to get them down over many months on subsequent Soyuz flights. So it's not an ideal solution, but it was the ace in the pocket, if you will. I kind of think that if we ever ended up in a serious damage condition, we might want to consider just bringing back a skeleton crew, maybe the commander and pilot and flight engineer, and allow the others to ride it out aboard the International Space Station. It would be less of a drain on the resources up there as well. That was never philosophically agreed to, of course. It was kind of a tough decision. Do you believe in the repair enough to fly the entire crew back, or don't you? And so that was a debate that we never really got into, and thankfully we never had to.
So the way we communicate risk to the mission management team is through our hazard report documentation. So leading up to STS 114 and 121, we developed a very in-depth set of hazard reports where we went through each one of the potential hazards that you would experience, that you could potentially experience from performing a repair. We addressed in very specific ways. Now, each one of those hazards was unique, and we had unique hazards between the different repair techniques, the plug repair and the crack repair material, the NOAX. And we documented in those hazard reports a lot of testing, a lot of analysis, and basically everything that we did and all of our shortcomings. So in a lot of different cases, these hazard reports ended up and some amount of risk being accepted by the program that we would go and address during the real-time flight situation. So we would never know ahead of time whether or not a repair would be good prior to performing the repair. Just a lot of that, the data that we would have to get to determine if that repair was good or not would be a real-time data point that we would have to collect from either the orbiter boom sensor system or from the crew themselves after performing the repair. So essentially we would take all of that data that we would get at different times. Again, we're collecting thermal environment data all the time. We're collecting different data that's coming in from the LESS PRT, where that's characterizing the damage. Essentially, we're getting data from the repair itself. We're getting data from after the repair, again in the form of thermal environment data. We're taking all of that data, collecting it, comparing it to how well did we address the risks that were left over in those hazard reports. How well did we cure their material? How well did we perform the repair? If we did a plug repair, did we get the gaps between the plug and the RCC down to the expected size? And then we would communicate all that data back to the mission management team, and either yes, we met this criteria, we didn't meet this criteria, we performed the following analysis and determined that based on all the data that we have, test data and analysis, that even though we may or may not have met everything to the letter of the law, here's what we feel about it, and here's our recommendation about whether or not we feel this is a good repair or not.
One of the difficulties with having repair concepts that are at a low technology readiness level is you're going to have differences of opinion on, say, the viability, and because you have a lack of data, there's going to generate controversy within the team as to, are those materials really ready? When are they ready for prime time? When are they ready to be manifested? And there were a difference of opinions at the beginning. There were issues associated with the materials that we had selected. The TZM material for the plug repair, we had concerns from the SNMA community. They had written a white paper basically saying that, hey, this material becomes brittle and can be fractured while you're on orbit, while you're trying to install it, and that becomes a risk. Or even when you're re-entering, may not be able to take the entire load that's imparted onto it. So these were concerns that were brought up to us, and managing through those, I'd say, controversies, discussions was very important, because we didn't want to, we wanted to learn our lessons that dissenting opinions were important, that our SMA counterparts or basically any other engineer on the team who had a concern, that we could address them, we could work through them, try and identify the right tests that would or mitigation plans to address those concerns.
One of my key personal takeaways from this is really the human element to this whole project. When I was first asked to come and manage the RCC repair project from the engineering side, it was a daunting task, and I have to say that I was mainly involved in the development of tools and equipment prior to that, and I had not had a lot of experience in aerothermal analysis, and certainly not the design and repair of the shuttle wing leading edge. And so when I really started thinking about that problem, I have to say, I mean, it was uncomfortable. I was a little bit worried about the way I was going to manage that whole project. But when it came down to it, I didn't want anybody else doing it. I mean, these are my friends that are flying on the vehicle, and I wanted to be the one to actually be there and develop those different techniques. I didn't trust anybody else to do that for my friends, essentially. So I had people that I knew on the very first two flights after the Columbia accident that I wouldn't have had it any other way. If you have any questions about anything that we've talked about today, just please feel free to contact me, Ben Greene, at the Johnson Space Center. I'm part of the engineering directorate here in Crew and Thermal Systems Division.
One of the big lessons I had learned through this, going through the repair project and seeing it to success, was the value that we had in the team members and learning how to divvy up the roles. We had to learn how to, especially for mission support, how do we work with each other and how do we trust and rely on each other to all come together to ultimately make a recommendation and to the project. And a lot of that was building trust with each other in terms of our technical discussions, even personal relationships that we had built up. Those were invaluable. At the end of the project, I felt confidence not only in the data that we had generated, the design concepts that we had developed, but really in the personnel that we had built up around this project. We had very close relationships in terms of building confidence in each other so that we could accomplish, a potential repair. If you would like any more information on RCC or RCC repair, feel free to give me a call. I'm Alvaro Rodriguez. I work at the NASA Johnson Space Center and the engineering director.
So the key takeaway for me from this project is the fact that it's the entire organization. It's a team. It's a people. Without the entire team, we would not be successful. However, within a team, it's how we manage the team. Each team member, we establish roles and responsibility early in the project. We all understood what each person is working on. Okay, we had developed the trust between all the members. Through time, we developed trust. I wouldn't say we developed trust at the beginning. Through time, we were able to trust each other, and it made my life a lot easier, make everybody's life a lot easier. As a project manager, I had to deal with not just the engineering folks, not just the technical folks. I had to deal with contractors. I had to deal with our contractor in making the plugs, the ATK Thical folks making the plugs. I had to deal with their subcontractor, GE. I had to deal with our Marshall folks, who is the one that developing the NOAX repair. I had to deal with the Langley folks for doing all the tools, as the drilling tool, as well as the technical experts there. And I had to deal with our KSC folks, our technical team, regarding what the effect is on the RCC panel as well as the aerothermal part of it. So, and the way I looked at this, the takeaway is making sure that you as a project manager listen to the people and make a decision based on their inputs. No one is an expert on everything, okay? So let's go ahead and listen to the expert that you trust, take into those information, make the best decision that you can make. Not with 100% information, you're never going to get 100% information. If you can make 80% information with 80% of the data and make a decision, that would be a good thing to do. However, the key is how you manage dissenting opinions. Another takeaway I got was that often when I had dissenting opinions, I would sit down with the individual and I'll try to understand what is actually concerning them. What actually makes them so objective to what we are trying to accomplish. Once you understand the true root cause of their discomfort, then you are able to then reach a compromise into developing new technical testing series, for example, to demonstrate that, hey, I had addressed this concern. For example, TZM is a very, very good example. We had issues with dissenting opinion from SNMA regarding the material. So we were able to communicate with them, and then we actually done additional testings and did additional analysis, try to answer the questions. At the end, I wouldn't say they were 100% satisfied, but at least they understand that we try, and that's the best that we can do to come up with the solution we currently have. So again, it's never really technical. Technical is something that we can all do, but usually from a project perspective, it's always going to be the people, how you manage the team, how you manage expectations of your upper management, how you managing your communicate with the people that work for you, and how much do you trust. Now, at the end, as a project manager, you had to make decisions. And there are times you had to make difficult decisions that nobody would like. But you had to make it because of budgetary constraints, because of time constraints, because of other issues. So good luck to everybody, and do the best you can. And again, my name is Frank Lin, And I was the project manager for RCC repair project. And if you have any questions regarding the repair project or any advice regarding future projects, give me a call. Contact me.
There are two major lessons learned that I'd like to share with future generations of space explorers, engineers, astronauts, whoever they might be. One is it's really, I think, good judgment, a good principle to have the crew compartment above any debris sources on ascent. We reviewed those shuttle ascent tapes over and over and over again, and it takes your breath away every time you see that little puff of smoke and you know what was actually happening then. So to have the crew compartment out of harm's way for the ascent trajectory, to me, is a fundamental design driver. And then secondly, I would suggest that as we venture out beyond Earth orbit, if we go back to the moon, onto Mars, places even beyond, perhaps even Europa, you really need to have the capacity within your crew and within the infrastructure that you take with you, the tools to fashion a repair that you've never ever thought of before. And I hearken back to my STS-120 solar array work, where brilliant engineers on the ground dumped everything that we had aboard the shuttle station complex out on a table and said, what can we fashion a repair out of using the stuff that they have aboard the station? If we didn't have 12 gauge wire stock and aluminum shim stock and all these other things to pick and choose from, we would have been out of luck. This is really an on-the-fly type of a repair. We had folks that you had the ability to follow the repair solution that had been uplinked from the ground, and then we had the capacity using the OBSS inspection boom to get an astronaut out to do the solar array repair. We can't imagine what might happen to a habitat on Mars or to an asteroid approaching vehicle. You just have to have a good toolkit to draw upon, and ideally a crew that is resourceful, because I think in terms of going to Mars with the time latencies that are going to be involved, the crews are going to have to be much more autonomous, not only in EVA but in terms of medical care, in terms of IT, computer repair, and all the other things that might befall a crew out there. So if you have any additional questions on anything that I've discussed here today, feel free to reach out to me through my website. It's www.parazynski.com, Parazynski.
So what we have here is an actual flight article which we factory flew on STS-114 with all the plug repair hardware for the RCC repair. What we have here is essentially there are a total of 19 plugs that's in this bag right now, but on STS-114 we actually flew only 13 of these. The plugs look similar like this. Because of the different curvature on the RCC panels on the vehicle, what we had to do is we had to go ahead and design different curvatures RCC plugs, and as we install them, here's an example. As we actually assemble the repair plug and we put it through, we drill the hole in the RCC panel, we insert it through, as an astronaut would do. As we torque up this bolt on the top, as the astronaut turn it, this T-bolt here will actually move up, and it actually becomes perpendicular to this shaft right here, eventually draws up to the backs of our RCC panel, very similar to what you would do normally at a home repair for a drywall repair. Similar concept. It's exactly what it would do. Okay. Once we do that, the astronaut will continue to torque it until this plate conforms to the RCC panels. We do have a gap gauge that we use to make sure that the gap does not exceed, I believe, 20,000, okay, of a gap. Okay. In addition to that, what we have learned doing testing was that to ensure that we do not have excessive gap, or we don't want any gap at all, we also use our crack repair material as sealant around the edges to give us additional confidence. In addition to sealing the edges, what we would also do is we also put a dab of the NOAX, or repair material, on top of the bolt. This would provide us additional thermal protection on the bolt to keep it cooler. Okay. So, like I mentioned before, there are about, we actually have total 19 different curvatures. The first 13 that we flew have curvatures like this or like this. Okay. But what we did was, as development of this, the design of our CC plug repair continues, what we found out was that the initial design that we had wasn't the most optimal design. What we ended up doing was, by reorienting the fabric as we manufacture the plugs from 90 degrees to 60 degree layup, we were able to produce only 6 plugs to cover 90% of what 13 plugs would have covered.